Sure what that was. Alrighty. So, first of all, as I've said at the beginning of every class since the first class, or maybe the second class, for anybody who just got in off the wait list, it'd be nice next week where I don't have to say that anymore. To anyone just got off the wait list, first of all, welcome. Second of all, you got some catching up to do. So, in the on Learn, there's a folder that says Math A01, or not Math, just says A01 and A04, and Harlan, that's me. In there, you should see a link to a YouTube playlist that has the intro video as well as, you're not doing this, as well as Thursdays of last week's class, as well as Tuesday's class for you to get caught up in reading. Also read the course outline. And to the new students who just got in and everybody else, on Crowdmark, you should have received a link. Granted, if you just registered in the last day or two, you'll be receiving the link later today or tomorrow to the Crowdmark with the honesty declaration. That needs to be filled out before the assessments begin. Granted, that's still a couple weeks away, but I was looking on the site yesterday, and about a third of people have actually done it. So about 2/3 of people haven't done it yet. So there's no reason to wait. I strongly encourage people to do that sooner rather than later. Otherwise, you get busy with other things, you forget, then you get a 0 on your first test, then you get upset, and yada yada. Nobody wants any of that. All right. If you do have any questions, feel free to fire them off. Otherwise, we're going to finish off the example we were talking about on Tuesday. So on Tuesday, we had this system of linear equations that we were solving. It was our first example of using our Gaussian elimination technique to solve it. And Gaussian elimination means we want to take this matrix and put it into row echelon form. So we did that. We started with our augmented matrix right here. We performed row reduction steps, and eventually we got it down to row echelon form. And then we ran out of time, and so we stopped. So my first question to you is is this in reduced row echelon form, or is it just in row echelon form? Not that. This. Is that matrix in reduced row echelon form or just row echelon form? So the chat is flying with just row echelon form. So we have two options here. The first option is called Gaussian elimination, where we're finished. And we're going to solve it based off of this matrix right here. The second one, so let me just write it out. So Gaussian elimination is just get it into row echelon form. Then there's Gauss-Jordan elimination, which says that's not good enough. We want to put it into reduced row echelon form. Now, I did get a message, a couple people after class, but also a couple emails for people who did this before we started talking about it, which is great, and got a different row echelon form. And I want to make sure that that's known that different matrices can have different row echelon forms. So if you might have gotten a different row echelon form than what we did because you did slightly different steps, that's perfectly okay. What you should notice is our solution in the end is the exact same solution, but the row echelon form could be different. That being said, if you put it into reduced row echelon form, it won't be different. Yeah, exactly. There's only one reduced row echelon form for any matrix. There could be many different row echelon forms. All right, so we're going to do this both ways. We're going to do this straight up using Gaussian elimination, where we're going to get our solution right from this matrix. And then we're going to, rewind ourselves a little bit and also do it using reduced row echelon form. All right, so we're in row echelon form. So here's leading one, number 1, leading one, number 2, and leading one, number 3. So what are our, first of all, how many solutions are we going to get to this equation? You can answer that from its row echelon form. How many solutions are we going to get? Maybe I didn't phrase my question well. Yeah, not how many free variables are we going to get, but how many solutions are we going to get? We're going to get infinitely many solutions. Infinitely many solutions to our 6 variables. Absolutely. All right. So do we have any free variables? And if we do, to which variables are free? There was no y's in our equation, so that doesn't make any sense. Right. So we're going to get a free variable for this column. We're going to get a free variable for this column. We're going to get a free variable for this column. So we get a free variable for every column that didn't have a leading 1. So every column that didn't have a leading 1 is going to be a free variable. It's going to be given a parameter. So x2 is equal to, let's say, r. x4 is equal to s because it's the 4th column. x5 is equal to t because it's the 5th column. So we get a parameter for every column that didn't have a leading 1. And then for each row that did have a leading 1, we're going to get an equation that's going to solve for the other ones. So the first equation, because we had a leading 1 for x1, that's going to give us our solution for x1. Same thing for x3, same thing for x6, although we'll start with x6 because it's the easiest one. All right, so we get a parameter for every column without a leading 1. All right, so let's start with row 3. What does row 3 say when we turn it back into an equation? That one says x6 is equal to 1/3. Boom, done. We have x6. All right, what about the second equation? What does that say if we turned it back into the equation world? So x3 plus 2x4 plus 3x6 is equal to 1. And we want to use this equation to help us solve for x3. Using the fact that we already know what x6 is, we just did it above, and we already know what x4 is, we have that above as well. So that's x3 plus 2 times x4, which is x, plus 3x6, so that's 3 times 1/3, is equal to 1. And now we're back substituting the stuff we already knew in order to solve for the x3. 3 times 1/3 is 1, so those 1's cancel. And so we get x3 is equal to negative 2s when we move everything else to the other side. So we had our 3 parameters. We have x6 from the third equation, and with a little bit of work, we have x3 from the second equation. All right. Any questions about how we got x3 before we move on to the only row we haven't used yet? All right, and what's the first equation say? The negative 2? Oh, did I write something wrong? I don't see a -2 in row 3. Oh, column 3. Oh, yeah. I mean, that's part of row 1. We haven't dealt with row 1 yet. That's coming next. All right, so what does row 1 say? X1 plus 4x2 minus 2x3 plus 3x5 is equal to 0. And we're going to do the same thing. We know x5, it's right up here. We know x3, we just figured that out. We know x2, it's up here, and we can use it all to solve for x1. So that says x1 plus 4x2, that's 4r, minus 2x3, so that's -2 times -2s, plus 3x5, which is 3t, is equal to 0. And if we move everything else to the other side, that's -4r, -2 times -2s is 4s, so the other side is -4s minus 3t. Right. So put that whole thing together, and we get our solution is x1, -4r minus 4s minus 3t, x2, which was r, x3, which is minus 2s, x4, which is s, x5, which is t, and x6, which is 1/3. So from its row echelon form, we can do the work with some extra substitutions, but we can do the work that's going to allow us to solve for this system. All right. If you have any questions, feel free to fire them off. I know I already see one. I'll get to that in just a second. If not, try to take that last matrix and put it into reduced row echelon form, and then see if you can come up with the same solution that way. Why is x6 equal to 1/3? Because of this row right here. So that row says 0x1 plus 0x2. They're called parameters. 0x1 plus 0x2 plus 0x3 plus 0x4 plus 0x5 plus 1x6 is equal to 1/3. That's what this third row is saying if we went from the matrix back to an equation. In other words, x6 is equal to 1/3. Any other questions? All right, so let me put that matrix back. 1, 4, -2, 0, 3, 0, 0. 0, 0, 1. I've already forgotten what it was. It's a lot of numbers. 1, 2. There we go. Alrighty. So, as was mentioned, we're not in reduced row echelon form. And what numbers in this matrix are making it so that we're not in reduced row echelon form? What two numbers would have to change in order for us to no longer be, or to actually be in reduced row echelon form? So this -2 is preventing us from being in reduced row echelon form, and this 3 is preventing us from being in reduced row echelon form. Everything else is fine. So let's switch them. I'm going to get rid of the 3 first. So row 2 is row 2 minus 3, row 1. And by row 1, I mean row 3. So the thing about putting it into reduced row echelon form is that it usually takes a few extra steps to put it into reduced row echelon form. So there's a little bit more work with the matrix in order to put it into reduced row echelon form. The trade-off is that it makes solving from the reduced row echelon form a little bit easier. So there's a bit more work in the matrix, a little less work in the solving afterwards. Right. As for this -2, row 1 is row 1 plus 2 row 2. And we get our double REF. Right here. All right. So in this case, 2 extra steps to put it into reduced row echelon form. But, oh, yes, for sure. Thank you. 4. A couple extra steps to put it into reduced row echelon form, but a little bit less work afterwards in order to read off the solutions. All right. So any questions about now that someone fixed my typo? Any questions about the steps to put it into reduced row echelon form? Or, there's 175 students in this class. So. All right. Oops. Hope that's exciting. That is not this class. All right. That being said, everything we do now is the exact same thing we did before. Right? So the first thing to note about REF versus RREF is that the leading one should be in the exact same place as any REF. So the leading ones are the same. The free variables are therefore exactly the same. So there's really very little difference in how we set things up now versus how we set it up before. Can you answer an REF versus RREF? Depends on what the question says. If the question says use Gaussian elimination, or if the question says use Gauss-Jordan elimination, then you have to do it that specific way. If the question just says solve the system, then it's up to you. But as always, do what the question asks. All right, so our three columns without leading ones stay exactly the same. So we still have free variables for columns 2, 4, and 5. Our third row is exactly the same, so we still get x6 is equal to a third. But our second row is easier. So what's our second row say now? Our second row now says x3 plus 2x4 is equal to 0. And so we get x3 is negative 2s right away. When we did it before, we had 2 extra terms. We had to substitute and simplify in order to come to this same conclusion. Now we've done all that work in the matrix, and so reading off the solution is a little bit easier. Similarly, with the first row, x1 plus 4x2 plus 4x4 plus 3x5 is equal to 0. And even though we have 4 terms here, except for x1, all the other terms have to be the parameters or the constant because everything else is gone. And so we get the same thing we got before, negative 4r, negative 4s, negative 3t. So that's the difference between Gaussian elimination and Gauss-Jordan. Gaussian elimination just get it to row echelon form, and then the extra back stuff will be dealt with the equations. Gauss-Jordan is do everything in the matrix, and then get it in reduced row echelon form, and then get our answers much more quickly when they go back to equations. All right, if you do have any questions about either of these, feel free to let me know. Fire it off in the chat. Otherwise, I'll come back to this. If you're still copying, I'll come back to that in just a second. Otherwise, give this question here a try and see if you can solve this particular question. The question's down here in purple at the bottom. Yep. Not equals to 0, though. But yes. I record every session unless I have some technical difficulties. Right, it's a function. It's a function. Y equals something. It's what a equation of a parabola would be, was y equals some expression there. All right. So some people are wondering where to start. Sounds like a reasonable thing. So we're trying to solve for a parabola here. We're trying to solve for an equation. Now, this might seem like a weird question considering this is linear algebra and a parabola is very much not linear. That being said, this is still a linear algebra style question. So we're trying to solve for the parabola. So what is the general equation of a parabola? So y equals ax squared plus bx plus c. So what are we solving for? If we're trying to solve for the equation of this parabola, what are we solving for? Right, we're solving for a, b, and c. So we're trying to solve for a, b, and c. And this is a linear equation if a, b, and c are what we're solving for. So while it might not look linear because of that x squared, it's not x we're solving for, it's a, b, and c we're solving for. So yes, this is a linear situation. So how do we solve for a, b, and c? We're going to plug in the points. So from the point 0, 1, what equation do we get using the point 0, 1? So y is equal to 1. and x is equal to 0, even though it might seem silly to write it with all the zeros, we get this equation right here. And from the other 2 points, we can get 2 other equations, hence 3 equations, 3 unknowns, and now we have the ability to solve for A, B, and C. So hopefully that's enough to get you going. I'll give you another minute or two to see if you can finish it off from there. But hopefully that's enough to get you going and realizing that this is linear because it's not x we're solving for. For the question that came way before that about the last one, so the column 3 with -2 before isn't a free variable. It was a free variable. Column 3 gave us a free variable. So something gives us a free variable if and only if there's no leading 1 in that column. Oh, sorry, column 3 did give us a free variable. My apologies. So column 3 was not a free variable. And the reason it was not a free variable is because there was a leading 1 in that column. So x3, unless I wrote something wrong, x3 was not a free variable in either situation. The free variables were x2, x4, and x5. In either situation, we used the second row to solve for x3 because we had a leading 1 in the third column. The only difference between the two situations is how easy it was to solve for that x3, but the fact that it wasn't a free variable had nothing to do with whether or not we were in RREF or just REF. During class time, no, I can't be solving suggested homework questions. If you want to ask me after class, I'd be happy to. It is not x squared plus 1. X squared plus 1 goes through the first 2 points, but it doesn't go through the third one. Same thing. Goes through the first 2 points, doesn't go through the last one. All right. So just like we did with the first equation, each one of these points sets up an equation that allows us to solve for A, B, and C. And so we get 3 equations with 3 unknowns, and that sets up this system. By the way, this 4 is because of 2 squared. This sets up a system of linear equation that's going to allow us to solve for A, B, and C. Now, I will say, full disclosure, because it came up as an issue when I was doing this with my other class yesterday, it's probably a bit overkill to be using a system when the first equation is just c equals 1. And I acknowledge that. I do want to do this as another practice of solving inside a matrix, even though I completely understand if people are realizing, oh, c equals 1 in the first equation, so we can plug it into the other 2. Absolutely, you could. So there's certainly nothing wrong with that. But I just want to do this as another example of some of our row operations just for practice. All right. So acknowledging what I just said, we have this system. if we're trying to put this into either row echelon form or reduced row echelon form, what do we need to do first? Why do you want to multiply row 3 by a quarter? Why do we need to turn this 4 into a 1? So where do we want to get our leading 1? Okay. Where do we want to get our leading 1? Right. We want to get a leading 1 right here. There are many different options. So one thing that was suggested in the chat is to multiply this row by a quarter. If you want to do that in order to swap it with row 1, that's perfectly fine. That will certainly work. I think there's an easier way, but that certainly does work. We could switch row 1 with row 2. I think that's probably the easiest way. Someone suggested taking row 1 and adding row 2. That also works. So there's many different ways, row operations, that allow us to turn this 0 into a 1. I'm going to swap row 1 with row 2, but don't take that to mean that the other ways people have been suggesting, those ways also work. So 1, 1, 1, 2, 0, 0, 1, 1, 4, 2, 1, 4. All right, now that we have our leading 1, what do we want to do with the rest of that column? Right. And we're absolutely going to do that. For what purpose? Row 3 minus 4, row 1. What purpose is that serving? Right, to turn the 4 into a 0. We want to make everything below that 1 into a 0. 1, 1, 1, 2, 0, 0, 1, 1, and 0. 2 minus 4 is negative 2. 1 minus 3, or minus 4 is negative 3. 4 minus 2 times 4 is negative 4. And now our first column looks perfect. All right. So any questions about how we made the first column really pretty? All right, then what's our next step? Switch the last two rows, again, for what purpose? I agree we should do it. Why? Right. So we want this thing, if possible, and that's a big if, but if possible, we want to turn that 0 into a leading 1. It's hard to turn zeros into ones because there's nothing you could add or nothing you could multiply by to do it. So we can switch the two rows to make this a negative 2, which can then be turned into a 1. All right, so somebody suggested, and I love the suggestion because it means I get to be a teacher for a second. One way to turn this negative 2 into a 1 would be to add 3 times the first row. Unfortunately, that causes a different problem. What problem would that cause if we added 3 times row 1? Yeah. While that wonderfully would turn the negative 2 into a 1, which is exactly what we want, it would turn this 0 into something non-zero, which means we're now going backwards in steps. So be careful here. If you have a leading 1 in the first row, when you move to the second row, I can't see a reason why using the first row to do anything to the second row is just going to cause problems earlier in that row, which we just don't want. So as much as it would have been nice to use this 1 to turn the negative 2 into a 1, unfortunately, it just doesn't work nicely. Some other people are saying multiply by negative a half. Absolutely. We'll take row 2 and multiply it by negative a half. And yeah, that causes fractions. Live with it. Can't always avoid fractions. All right. So now we actually, because the only thing left to do is to turn this into a 0 and this into a 1, which they already are, we actually have something in row echelon form, which means we could use the back substitution if we'd like. But for another practice, I am going to put this one into double REF. Yes, the 3/2 is positive. All right, so this question didn't specify Gaussian or Gauss-Jordan, which means if you want to, you can, stop at REF and then jump back into the equations. Although I'm going to keep going to put it into reduced row echelon form. So what do we have to do to put this into reduced row echelon form? Right, so we can use our leading one right here to get rid, and by get rid, I mean turn the things above it into zeros. So we take row 1 and take row 1 minus row 3. And we could take row 2 to be row 2 minus 3/2 R3. Somebody suggested turning this -1 into a 0 as well. That's perfectly fine. If you wanted to start with column 2 and deal with column 2 first and then move to column 3, certainly nothing wrong with that either. So there are a variety of different steps that can get you into reduced row echelon form. Anyway, so this 1 minus the 1 is 0. 2 minus the 1 is 1. 3/2. So this would be 2 minus 3/2 times 1. So that is 1/2. 0, 0, 1, 1. And then now we can take row 1 and subtract row 2. Why would we touch row 1 with row 3 when it does not need a 0 in the top row of column 3? Again, it depends on which method we're using. So if we're just using Gaussian elimination, if we're just making it into REF, then you're right. We wouldn't touch it. We'd stop right here and jump to the equations. If we're using the method of putting it into reduced row echelon form, then we do need it to be 0. And that was what we're practicing with these last two steps, was to make that happen. So both are valid methods. This question didn't specify one versus the other. So if you wanted to stop and then jump back to the equations, it'd be a little bit more work in the equations, but it would still answer the problem. So the first row says A equals 1/2. Second row says B equals 1/2. Last row says C equals 1, which we knew from the beginning. And so, as some people mentioned, y equals 1/2 x squared plus 1/2 x plus 1. And we have our parabola. All right. So any questions about how we can solve a system of equations? Why exactly can you change a single number in a row? Wouldn't it change an entire row? Absolutely, it would change an entire row. So if you're wondering from this step here why it just changed this 1 into a 0, it didn't just change the 1 into a 0, it also changed this 1 to 1/2. The reason it didn't change the other numbers is they were zeros, so zeros aren't going to change anything. Sure, and like I said, there's many different steps we could have done to get to this. All right, so somebody got a different answer. That's not surprising. I mean, things happen. How can we check if our answer is correct? Plug in the points and see if you get an answer. One of the nice things about solving systems is it's an easy thing to check at the end. It's much harder to find your mistake if you made one, but it's something you can check in the end. You just plug back in the original points, and if if all 3 points satisfy the equation, we're good. If one or more of them don't, then too bad. We do require the techniques that we teach in class or what we're testing on tests. So we are expecting these methods that we're learning in class to be used on the assessments, yes. Any other questions? All right, so that's how we're solving things. So I just want to end this section just by talking about a few theoretical things. Everyone loves theory, so let's talk about this one right here. So I claim that a homogeneous system of linear equations is always consistent. So let's make sure everyone's on the same page. What does it mean again for a system to be consistent? Has at least one solution. Has at least one solution. Great. What does it mean for a system to be homogeneous? Yeah, so to be homogeneous, the right-hand side of every equation is equal to 0. Someone ruined my punchline, but that's fine. If you're ruining my punchline, that means you're thinking. xn, xn, xn equals 0. Beautiful. So back to the question. So is a homogeneous system of equations always consistent? Yes. And why is that? Right. Since we always have a solution, a homogeneous system means we have zeros on this right-hand side. And because it's homogeneous, we're guaranteed to always have a particular solution. Specifically, the solution, people are calling it the trivial solution, which is absolutely true. What is the trivial solution? What's equal to 0? Just 0 is not... everything? Yeah. The x1, the x2, all the way up, all the x's are equal to 0 is a solution. So a homogeneous system is always consistent because what we call the trivial solution, where all the variables are equal to 0, if we plug that into every single equation, the left-hand side would be 0 every single time, which would equal the right-hand side. So all the variables being equal to 0 satisfies the first equation, the second equation, the third, the 8th, the 15th, the 2007th. It satisfies every single equation, and hence it's a solution to this system. What don't we know until we actually start row reducing? If we know that this is a solution, what don't we know until we start row reducing? Because that seems like a lot of stuff to know before we even do any work. No, given a system, we know whether or not it's homogeneous. Yeah, what we don't know is if it's the only solution. We'd have to check. If we want to know if it's the only solution, we'd have to check, are there free variables? Can we row reduce? All that work would still have to be done to figure out if it was the only solution. But we know for sure for a homogeneous system that we get a solution, namely the trivial one. Whether there's more than that, I guess we'll have to figure that out. All right, what if we just change? What if we removed that it was homogeneous? What changes if all of a sudden it wasn't homogeneous anymore? Could we say the same thing? What would change if it was not homogeneous? Let's say this was a 5. Could we still say that we're guaranteed to be consistent? No. Why not? What could happen that couldn't happen before? Right. First of all, the trivial solution is certainly not a solution anymore. And what could go wrong because of that? When we row reduce. If we have a non-zero in the right-hand column, all of a sudden it's possible to have 0 equals not 0. In which case it's possible to get an inconsistent system. All right. So one more question. So let's go back to homogeneous. And now let's say we had more unknowns than we had equations. So let's say there were more unknowns than there were equations. So we definitely get a solution. That hasn't changed because it's homogeneous. I claim we get more than, or we know more than that. What are we guaranteed if we have more unknowns than equations? Why are we guaranteed infinitely many solutions? I agree. We're guaranteed infinitely many solutions. Yeah. If we have more variables than we have equations, then we would have to have free variables. We can only get a leading one for every row. So if we have more variables than rows, then we're guaranteed at least some columns without leading ones. Meaning we're guaranteed that we get infinitely many solutions. So an interesting thing, if we have a homogeneous system with more variables than unknowns, we know before we even start that we get infinitely many solutions. Of course, to find the solutions, you got to actually do the work. But before we even start for a homogeneous system with more equations than or variables than unknowns, we're guaranteed to get infinitely many solutions. And we don't even need to do the work to know that. Right. What if it's not homogeneous? Are we still guaranteed infinitely many solutions? Are we still guaranteed a free variable? I mean, in theory, we're still guaranteed a free variable, but what could go wrong if it's not homogeneous? Right, there could be no solutions. It might not be consistent. So more variables than unknowns, than, equations. If it's homogeneous, infinitely many. If it's non-homogeneous, then we could have no solutions. It's not homogeneous if at least one of the equations is non-zero, is not equal to zero. So the moment there is one or more of the equations where the constant is non-zero, then it's not homogeneous anymore. So if we have more unknowns than equations, then we're guaranteed a free variable. Right? More columns than rows. There's got to be a column without a leading one. Which means if it's a homogeneous equation where we know it has a solution, then there's infinitely many. If it's not homogeneous, then we still have a problem where it might not be consistent. But if it is consistent, then there's infinitely many. Again, so these are just things that we could see from the equations. There's stuff that's going to periodically show up throughout the course where there's going to be times where we can immediately know how many solutions we have. Now, none of this will tell us what the solutions are. But there are times where all we care about is how many solutions we have. And we can get that sometimes without actually having to do any calculations. Right. Questions about the more variables in equations? All right, what if there was the same number? What if there was the same number of equations as unknowns? Can we guarantee anything? Can we guarantee exactly one solution? Just the trivial solution if it's homogeneous? Yeah? Oh, we can certainly guarantee at least one. If it's homogeneous, we can guarantee at least one. Can we guarantee it's exactly one? No? Why not? The same number of rows as columns. How could we possibly get a free variable if we have the same number of rows as columns? Bingo. If this was our system, what happens? If this gives us our system, two equations, two unknowns, but what happens? Yeah, one of the equations is redundant. One of the equations is redundant. So even though the original system looks like two equations with two unknowns, it's really kind of one equation with two unknowns. Because one of the equations is redundant, and then we go back to what we just talked about. But a different system could turn into this. So if we have the same number of equations as unknowns, it could be infinitely many solutions because we have a free variable. But it might not be infinitely many solutions because it might not have a free variable. The point being is we can't know that ahead of time. So if there's more unknowns than equations, we get a lot of information. But if there's the same number, unfortunately, we can't draw any conclusions to begin with. Homogeneous or non-homogeneous. So we get nothing. So this doesn't help us at all. But this is a nice one, because in this situation, we know exactly how many solutions there are, and we don't even need to do any work, which is kind of nice. All right, if you do have any questions about these ideas, please let me know. Otherwise, someone was begging for some matrix operations earlier in the chat. So Here's some matrix stuff, and feel free to try some of these properties. Maybe that'll be a little bit less headache inducing. But if anyone still has any questions about the last one we were doing, feel free to keep firing them off. If you're comfortable moving on, see if you can give these questions here a try. It would be no for both of them. So it's more of a maybe versus a definitive yes or no. Like, maybe it'll have exactly one solution, maybe it won't. If there's the same number of equations as unknowns, maybe it'll have one, maybe it'll have more. We'd actually have to look at the specific. We'd have to look at the specific equation in order to be able to answer that. The last question on the previous slide was just what if it's not homogeneous? So we talked about that as well. So for the first two, it was no, because the possibility of being inconsistent was true if it was non-homogeneous. And as for the last one, we never know anything ahead of time in that case, homogeneous or not. All right, so a lot of people are saying the fourth one is not possible. So since everyone wants to focus, and by everyone I mean the 3 or 4 people who typed it in the chat, seems to want to focus on the fourth one, we'll start there. Why is A plus B not, why is A plus B not possible? Something like number of rows or columns. So in this case right here, we have a question that says, if it doesn't exist, give a specific reason. So I want to be clear about what I mean by that. So saying the number of rows and columns is not specific enough. We have to be very specific as our reasons. So some people are saying they're not the same size. That's perfect. Just saying the rows don't match, or if this will come up a lot more with multiplication, but the rows don't match, or the columns don't match, or the stuff like that. We want to be very specific as to our reason why it doesn't matter, or why it isn't possible. So what is the size of A? Yes, size does matter. So A is a 2 by 3 matrix. So the first number is the number of rows. The second number is the number of columns. A is a 2 by 3 matrix. B is a 2 by 2 matrix. Since it's 2 by 2, what else do we call? That means that B is what type of matrix? It's square. Very good. And since the sizes are not the same, so I guess I should say we're answering 4 right now. Since the sizes aren't the same, A plus B is not defined. But we're being very specific here as to the reason. We're not just saying they don't match. I can't tell you how many times I've seen students say, you can't do it because that doesn't match. I'm like, why doesn't? Like, what about it? Let's be specific as to our reasons why something does or doesn't exist. All right. As for A and C, they're both 2x3 matrices, so we can add and subtract them all we want. But if their sizes aren't the same, then we can't add them, we can't subtract them. We might be able to multiply them, but we'll get to that in the next example. All right, as for 3b, you can multiply any matrix by a constant. So what's 3b equal to? Multiplying by a constant is fairly straightforward. We're just multiplying every entry inside that matrix by that same column, constant. So 7 times 3 is 21, 8 times 3 is 24, 9 times 3 is 27, 10 times 3 is 30. Multiplying, as you know, unless you make some arithmetic mistake, multiplying a matrix by a constant tends to not be the most complicated thing. Multiplying matrices is the complicated one, and we'll get to that. All right, what about A plus C? They're both 2x3 matrices, so we can add them together. And I lost it off the top of the screen there. So actually, let me write them out because I did lose it off the top of the screen. 4, 5, 6. Yeah, so again, assuming the sizes are the same, and the sizes need to be the same before we do anything, but assuming the sizes are the same, we just add them together an entry at a time. So 1 plus 11 gives us 12. So the adding of matrices is fairly straightforward. 2 plus 12 is 14. And we just keep going. 16, 4 plus 14 is 18, 5 plus 15 is 20, 16 plus 6 is 22. Any questions about how we add matrices together? All right, for 3, 2c minus 3a. So now we're just combining them together. 2 times c. Multiply everything in c times 2. And subtract 3 times a. So 3, 6, 9, 12, 15, 18. So any matrix can be multiplied by a constant. Eventually we're subtracting. So what needs to be true again in order for us to be allowed to subtract? Right. The sizes need to be the same. In this case, 2 by 3, 2 by 3. The sizes are in fact the same. And now it's just some grade 3 subtraction practice. 19, 18, 17, 16, 15, 14. So, again, the trickiest thing about adding, subtracting is just making sure we're aware of when we are allowed or not allowed to subtract them. The actual subtraction or adding or even multiplying by constants is, you just take each entry and look at them one at a time and combine them together in whichever way the question asks. All right, so any questions about adding, subtracting, or multiplying a matrix by a constant? All right, so the complicated one. So here's a whole bunch of matrices right here. Now we're going to multiply these matrices together. So again, I'm going to give you some time for this one because it's a little bit more work in them. Give these ones here a try. And again, find them if they exist. If they don't exist, give a specific reason. Not just the sizes don't match. Give a specific reason as to why you can't actually multiply them. People want to jump to the ones that don't exist a little bit. So I guess if people want to focus on the one that doesn't exist, we might as well get that out of the way first. CA doesn't exist. So this is number 4 again. That's coincidental. CA doesn't exist. And why is that? Right, because the number of columns of C is not equal to. Some people are saying is bigger than. The number of rows of A. Right. So in order for the multiplication to be defined, and the way we multiply them is why we need this, is the number of columns of C must be equal to the number of rows of A. Now again, we want to make sure we're being specific here. Just saying that, C is 2 by 3 and A is 2 by 2, I mean, that's a very true statement, but that doesn't explain why the multiplication is not defined. So making sure to get this statement in here is important, not just that it doesn't exist, but exactly why it doesn't exist. All right, so in order for multiplication to even be defined, we need the number of rows of the first matrix to match the number of columns of the second. All right, we may not get through all of these, but we can at least get started. So for 1, AB is 1, 2, 3, 4 times negative 1, 2, negative 3, 4. All right. So the number of columns of A is 2. The number of rows of B is also 2. They match, so our multiplication is defined. So if I want to find the first row, first column entry of the product, what do I need to do? How do I find the first row, first column entry? So if we want to find, call it AB11, the first row, first column entry, we take the first row of A and we multiply by the first column of B. But unlike addition and scalar multiplication that were very easy, this is a much weirder process. It's not just take the two entries and multiply them together. It's taking a row and multiplying by a column. In other words, what do we get for our first row, first column? We're getting -7. So we take 1 times 1, -1. I'll write it out in every gory detail at first. We take our 1 times -1, and we add 2 times -3. And that's how we find our first row, first column entry, is we take the first row of A times the first column of B. And if the number of columns didn't match the number of rows, well, then this just wouldn't be possible. We'd have more things in one than the other. Right. So that's how we multiply matrices, is we take the individual rows and multiply them by the individual columns. Right. Any questions about that idea? Because this would eventually just be -7 anyway. All right, so first column, first row times first column gives us -7. For first row, second column, we take the first row of A times the second column of B. And what do we get? We get 1 times 2 plus 2 times 4, which, as some people are pointing out, of course, is just equal to 10. Right. Second row times first column. What do we get for second row, first column? 3 times -1 plus 4 times -3, which is -15. That's right. And second row times second column would give us what? 3 times 2 plus 4 times 4. So, whoops. 10, -15, and 22. And that's how we multiply our matrices together. But we're multiplying rows times columns, not entries. That's the big difference between multiplying matrices versus adding and subtracting matrices. Adding and subtracting, we're doing entry by entry. For multiplication, we're doing rows times columns. So, much different process in order to get it done, but we can get it done. That not be 24? 3 times 2 is 6, plus 4 times 4 is 16. 6 plus 16, 22. All right, so we tried them the other way around. Again, if we do this, quick little check. 2 columns in B, 2 rows in A, so that's defined. We take our first row times our first column, and what do we get? Right, so -1 times 1 is -1, plus 2 times 3, -1 plus 6 is 5. First row, second column. Right. Negative 1 times 2 is negative 2. 2 times 4 is 8. Negative 2 plus 8 is 6. Second row, first column. Go 9. Negative 3 times 1 is negative 3. Plus 12 is 9. Careful there. Negative 3 times 1 is negative 3. Careful not to add them. And second row, second column is 10. So there we go. And we've managed to multiply them. So last thing, if you want to have any questions about this, feel free to stick around. I'll be happy to answer them. But one thing I want you to get out of this, other than how to multiply matrices, is up here is AB, down here is BA. What do we notice about those two? They're not the same. A times B and B times A are not equal to each other, at least not always. So keep that in mind when we're starting to work our way through these. Matrix multiplication is not commutative. You can't switch the order of any matrix stuff that we do from here on in. Well, for multiplying, you can switch the order of addition, but you can't switch the order of any multiplying of matrices. All right, we'll see more examples of this next week. If you have any questions, let me know. If not, have a good day.